In the last few videos we've been looking at solving linear second order differential equations with constant coefficients. We've considered the first type where b squared minus 4ac was greater than 0, the second type where b squared minus 4ac was equal to 0. Now we're going to look at the third type where b squared minus 4ac is less than 0. And we can look at these in two different cases, and they both give rise to a different result which we can quote in our work. We're asked to find the general solution of the differential equation, so we've got d2y by dx squared plus 25y is equal to 0. We know that this is in the form a d2y by dx squared plus b dy by dx plus cy is equal to 0, and this gives rise to what we call the auxiliary equation of am squared plus bm plus c is equal to 0. So in this case what we're going to now have is m squared plus 25 is equal to 0. All I've done is match this up, and this is what we've been looking at in the previous videos. If I wanted to solve m now, we can see quite clearly we're going to have no real roots. So subtracting 25 from both sides and squaring, I'm going to end up with m is equal to plus or minus 5i. In general, when we have purely imaginary roots, we're allowed to quote the following result in our work. We can state that the general solution will be y is equal to a cos, and then we will have now alpha x plus b sine alpha x, where a and b are arbitrary constants. That is a result we can quote. So in this case, all we would have, the general solution to our differential equation would be y is equal to a cos 5x plus b sine 5x, and that's that one sorted. So for example, now if we had say we had d2y by dx squared plus 81y is equal to 0, then we could write the general solution is y is equal to a cos 9x plus b sine now 9x. So nice and straightforward. That is if we have purely imaginary roots. So I believe that's in the formula book, but it's something that you can quote in your working. The second scenario, now we're asked to find the general solution of this case. So what we'll do is use the auxiliary equation of m squared plus 8m plus 17 is equal to 0. We need to solve this, so you can either use a quadratic equation or complete the square. I'll complete the square. M plus 4 all squared minus 16 plus 17 is equal to 0. So we can say now m plus 4 all squared, what we can have, plus 1 is equal to 0. So we can see again no real solutions. Subtracting 1 from both sides, square rooting, and then subtracting the 4, m will be equal to minus 4 plus or minus I. So there are your solutions, and I'm again assuming that you're cool with a quadratic where we've got complex roots. Now, if we have this form where we've got the roots now as p plus or minus qi, then our standard result, and again we can quote this, is e to the px, then we have a cos qx plus b sine qx. So if we look at what we've got here, we can see from our roots, in our case, p is going to be equal to -4, and then q is going to be equal to 1. So we could write the general solution now to this as y is equal to e to the -4x, then we would have cos, and unfortunately in this case we've got cos 1x, so it's just going to be cos x plus now on here, sorry, a cos x plus b sine x, and that right there is the general solution where a and b are arbitrary constants. Hopefully I've got another one, because I don't like leaving that with just the x, because it's not always going to be just for one. So let's see if we've got another one. Okay, let's go at this for a minute. So what we'll have on this auxiliary equation, we'll have m squared plus 4m plus 13, and set that equal to 0, so we need to solve this. So it's going to be what, m plus 2 all squared minus 4 plus 13 is equal to 0. So what's this one going to be? M is equal to negative 2 plus or minus, what are we going to have on here? That's going to give me 9, isn't it? So plus or minus 3i. So again, take your time to solve that. We can see in the case here, p plus or minus qi, we can see that p will be equal to negative 2 and then q will be equal to 3. So the general form is y is equal to e to the px, then we've got a cos qx plus b sine qx, and in this case the general solution is going to be y is equal to e to the negative 2x, there's your p, and then we're going to have a cos 3x plus b sine 3x, and there we go. General solution, a and b are arbitrary constants, and we're sorted. So we can quote this result, and again I think that's in the formula book. I'm pretty sure it should be. If not, if you can learn it, fantastic, and then just stick the values in. So there we go, that's where we wind up, and that's where we have the third case scenario where our roots are either purely imaginary or complex.